So I'm going to talk briefly about Greenwaves. We're a fabless semiconductor company that's based out of France, close to Grenoble, and talk a little bit about edge AI, which is a subject which a lot of people are talking about at the moment. There is definitely a movement of moving AI functions, so content understanding functions out to the edge of the network at the moment for a variety of reasons: cloud congestion, privacy concerns, particularly in the case of audio or video type information, making decisions quicker, and also power, reducing the power consumption of transferring data around. What Greenwaves is really focusing on is where we get to what we call the very edge, which is really onto devices which are either wearable, highly small, where in terms of cable and power availability, power is not around, so you need to operate on batteries, where they're distant from power or they're difficult to service. And some of the problems we have to solve once we get into devices of those types is that there are a wide range of different tasks that we're trying to carry out, and we have to scale the processor to those tasks. So a particular task might be the actual inference task, running an AI network, and that's going to require a high amount of computability. Another task might be just communicating, which is going to require a low level of actual activity in the circuit. So we need the circuit to be able to scale from this very, very high level of compute task down to a very low task. And in each one of those states, we're going to need the power consumption to be extremely low, otherwise it's going to drain your battery. And you're going to need to move between those states extremely fast, otherwise during the movement between the states, you're using up the battery as well. And those states can be very large amount of different types of things you're doing. Acquisition, acquiring the data, where you've got a lot of data moving around, but not a lot of processing. Some pre-processing, which is things like signal processing, preparing data to be able to do inference on it. So particularly sound and vibration sources, you'll need to prepare them. There's quite a wide range of different algorithms you'll do there. We also have a challenge, which is that the AI world is moving extremely quickly. There's new papers every month, new algorithms that are coming out. So we need something which is a device which is flexible enough to be able to match those. So the product that we've released, and we released this product actually at Embedded World last year, and have been shipping it out to customers since May last year, and are just going into production with it at the moment. It's called GAP8. The GAP8 is a chip. It's a highly integrated MCU that combines a 8-core parallel compute cluster with an MCU type controller. It allows you to provide very high compute at ultra low power. And when I say ultra low power, I mean versus state of the art on signal processing and AI algorithms, we're delivering about a 20 times energy efficiency gain. We're really focused on this level of power consumption when we're in a high compute state of underneath 100 milliwatts. In fact, top power that we're going to consume is going to be in the region of 75 to 80 milliwatts when we're really with everything switched on. It also combines this with an ability to switch between states in an extremely agile way. So we can wake up and be executing code in under a millisecond, half of a millisecond. And when we're asleep, when we're doing nothing, we're very, very low standby current of 1 microamp, which is definitely within the bounds of state-of-the-art in microcontrollers at the moment. Finally, it's a fully programmable device, so we can cope with accelerating anything that's really parallelizable. So there's a wide range of algorithms, and as the AI algorithms change, we can follow that change. An example of the energy efficiency, this is looking at a benchmark that was actually released by ARM last year, which was an inference on CFAR10 images. And basically, they had a graph, very quantized graph, 8-bit quantization. And they actually released this benchmark based on the STM-F7. We've restated it to the H7 from their data sheet in terms of power consumption. But they're both M7 cores. And they were able to do this inference at 216 megahertz in 21.4 million cycles. And that's took them a tenth of a second to do the inference at that speed, which is 21.4 million cycles. So they're consuming 60 milliwatts over that tenth of a second. If you do the same algorithm on GAP, so we ported an identical algorithm to GAP, we can do that algorithm in 1.5 million cycles, which allows us to drop our clock speed down to 15.4 megahertz, and the voltage, we can drop our voltage in the chip down, and that gets us to a 3.7 milliwatt power consumption, which is a 16 times reduction. That's only programmable functionality. If we boost our clock up to 175, which is our maximum speed, then we can run the algorithm in 8.7 milliseconds, which is an 11 times power performance increase versus the M7 core, and we're consuming 70 milliwatts, which is more or less the same amount of power. Then our chip, actually, we add extra blocks. And one of those blocks that we add inside what we call the cluster is a block that's able to do convolutions in a way which is extremely power efficient. It can do a single 5x5 convolution in a single cycle on 16-bit fixed point data. If we switch that device on and then use it in combination with the cluster, because this acts like a core, so we still have the parallelization ability for things which we might not be able to use that dedicated hardware block for, then we can actually take the clock speed down to 4.7 megahertz on average. We go down to 460,000 cycles, which allows us to take the clock speed down to 4.7 megahertz. And that gets us down underneath a milliwatt to do the same calculation, which is a 75 times power performance increase. How do we achieve this? A number of different things. Our design is based on cores which are based on RISC-V. We've extended the ISA of RISC-V, so at the individual core level, we achieve efficiencies by using the capability of the RISC-V instruction set to be extended. We use a variety of different instruction sections. DSP operations like single cycle loops, saturation operations, clipping, and so on and so forth. SIMD operations, so vectorized operations on 8-bit or 16-bit vectors. And we have a bit shuffler in each core, which allows us to do bit counting, bit shuffling operations. Secondly, then, at a more global level, we then combine the cores into a parallel cluster structure. This is a shared memory structure. It looks very much like OpenMP and hardware. And all of the thread dispatch, all of the synchronization in that structure is done in hardware with automatic clock gating, which again allows us to have very effective parallelism. And really, we're using parallelism to allow us to reduce the clock speed. Finally, other architectural attributes such as a shared instruction cache allows us to share the instructions that are loaded amongst the cores in the cluster. So we need to do one instruction fetch into the cache, and then we deliver that instruction to all of the cores, again saving energy. Finally, we have these hardware blocks that we can add, like the hardware convolution engine and the ultra-fast state changes by integrating all of the power management into the SoC. But this chip remains something which is programmable in high-level languages. You don't need to go to assembler. It's not a difficult architecture to program. We have a GCC-based toolchain which makes use of all of our instruction set extensions inside the optimizer. We have Visual ID. We also have a code generation tool that allows you to help with memory movements between the different areas of the structure, and a pre-built generators, which we've actually used that code generator to produce, which can do things like CNN layers, field filters, FFTs, all of the things that you'll expect in that kind of structure. It can be used in a wide range of different situations. Areas such as people and object counting from images, whether they be visual or infrared spectrum, doing high-speed industrial vibration monitoring or infrared monitoring for detecting faults and then just sending back a signal when that fault has been detected. In consumer products, to recognize people, to autonomously pilot, we have a small nano drone which can autonomously navigate using a CNN inside it. Then in smart building applications such as glass break detection or human sound detection, keyword spotting, and then a couple of uses augmenting an existing sensor. So for example, take a peer sensor which wakes up GAP, turns the camera on, takes the photo, checks if the thing that it's seeing is actually a human being or an animal, and then makes a differentiation of that. If it's an animal, goes back to sleep. If it's a human being, send a signal. So they're reducing false positives. And then kind of the inverse, which is we use gap to wake up something bigger. So if you've got a high-resolution camera with a very, very high-powered AI capability, we can be just spotting something as a steady state and then just wake up that larger system. And that's it. Thank you.